To introduce you the first speaker of this morning session, Patrick Speissegger, who is going to continue holomorphically germs of X, and his title sounds like a little bit Indiana Jones movie or Dan Brown novel. So let's discover Patrick Speissegger and the missing lecture.
The missing lecture. Thank you very much. Yeah, so this, like, in a way, this lecture is a continuation of my course from March. But of course, I know not everybody attended that course, so I do my best to give a lecture that makes everybody equally unhappy. That's kind of the goal here. Okay, so what we were discussing in the course, so I'm going to give a try to give a quick review of what we need to know. Right, we're talking about the Hardy field of germs at infinity of functions definable in Rn(exp). So I will not define Rn(exp). Right, we have heard a lot about this semester, so I think that will be taken as a given. Okay, and the question that I'm addressing here is to describe holomorphic continuations of these germs. Okay, so what? Yeah, well, in fact, not just holomorphic, but biholomorphic continuations. Okay, so well, what's the starting point for this? We know that Rn(exp) has analytic cell decomposition, so these germs are all analytic functions, and as such, they have some holomorphic continuation to the complex plane. The question is how far, what do those domains look like, what do these extensions behave like on those domains, okay? Especially where are they biholomorphic and what's the image, that kind of thing. Right? Why the image? Well, because being the Hardy field of a ominimal structure, it's closed under taking compositions and compositional inverses. So that comes into play when we are trying to study this, right? Describing these holomorphic continuations. So as it turns out, right, the optimal setting to study, or optimal as far as we know, to study these holomorphic continuations is not actually to the complex plane. So maybe I'll start with a picture here, right? Complex plane. Yeah, that's the origin right there. And let's say that's my usual half plane, right? Which I'm going to write h of 0. Okay. But turns out a better setting where we can get more precise statements is the Riemann surface of the logarithm, which I'm going to draw also as the half plane, right, using polar coordinates. So denote that by L, right? Of course, there's nothing at 0. That's why I'm drawing this line, only indicating the line. So a typical element here is denoted by x, okay, and has two coordinates. One is the modulus, which you write like that, and one is the argument. Okay, so the modulus is a positive real number and the argument is any real number. And as we know, right, this is a covering space of the deleted plane, so except for the origin, right? The covering map I'll denote by pi. Okay, so for example, when we look at what the picture looks like, the right half plane over there corresponds to a strip here, where everything is between argument pi over 2 and minus pi over 2. Okay, so this guy here corresponds to that guy over there. So for instance, if we look at, I will talk a lot about domains like this. Ilyashenko's domains that he talked about, standard quadratic domains, which would look something like that over here, right? Omega, standard quadratic. In this thing here, it will only look like something like that. So this is, again, a standard quadratic domain, U. Okay. All right. So the optimal setting is L. So extensions, or no, sorry, continuations F bar from some domain in L to L. Okay. So usually, yes, I just write F bar for such continuations. Right, I'm using, notation a bit because, of course, they're not unique. Right. Any questions at the moment? All make sense? Okay. Yeah. So, in order to describe these holomorphic continuations properties, right, we introduce a certain type of domain, right, on the Riemann surface. So what we call a real domain. Okay. So these are domains, and I'll be a little bit more restrictive than I was in the lectures, right? I'll just use real functions coming from the Hardy field. Okay, so for a function in the Hardy field that's positive, I'm going to look at the domain in the Riemann surface defined by the argument of x in absolute value being less than or equal, no, less than f of the modulus of x. Okay, so in fact, right, on the Riemann surface, they look a lot like those Ilyashenko domains, the standard quadratic domains. It could be something like this. They're symmetric with respect to the positive real axis. Right? Wow, these are all the same colors. They look different. Okay. Okay. So in particular, this standard quadratic domain is a real domain. Okay. But you can have real domains. Now I'm really trying to find different color. This could be a different color. Right? The real domains, most real domains will be like this. With the boundary function f going to 0. It's all possible. Right? So I have very small holomorphic continuations. Does that make sense? And so I will, of course, I don't really care about what these domains look like near 0. I'm only interested in their germs at infinity. In that sense, right, every such domain uniquely corresponds to a germ in H. Right. So that's really all I'm talking about. Okay. And so, right, what we'd like to do is we'd like to give a description of these holomorphic continuations in terms of how big these domains are. Okay. And for that, I want to use sizes that we already know about the germs themselves of functions in H. Right? There's sizing. Well, there's different types of sizing. This is all about asymptotic size at infinity. Right? Of course, there's the valuation, standard valuation that would be something like this, but that's way too complicated. I want the simplest sizing that we have of germs at infinity in H, and that's called the level. Okay, that's a very simple so sizing of germs in H. There's one, oh yeah, I shouldn't write here. I keep forgetting about that. Okay, so the first one, and that's not the right board, right, is the level, which was introduced, I believe, by Rosenlicht. Which is usually only defined on a subset of the germs, namely the ones going to infinity, plus infinity, or minus infinity, and takes just integer values. So very simple, right? And it just tells you the exponential growth rate at infinity. Okay. So I, right, being the germs going to plus infinity. Okay, so I won't define this here, right? It really says that once you apply enough logarithm enough times on the left to a germ, you become equivalent in growth to just an iterate of the logarithm, another iterate of the logarithm. And the difference between the iterates of logarithms you had to use, that's the level that's uniquely defined. Okay, the fact that functions in H have level, that's a theorem due to Miller and Marker. Okay, so I want to use that because it tells us roughly, right, the exponential function has level 1, log has levels -1, power functions have level 0, and so on. There's another type of size that I want to use. It's kind of similar. It's also integer valued, exponential height. But it's completely different. So that's defined on all of H. So to define this, we use the fact that germs in H are in fact all given by terms in the language of addition, multiplication, exp, and log, and composition with convergent power series. Okay, whenever that makes sense. And the idea is that every time you compose with exp, the height goes up by 1. You compose with log, it goes down by 1. Okay, so it's just a syntactic notion, which, of course, is not per se uniquely defined for a germ of a function, right? The function has many different representations as terms. So one has to do a bit of work to show that there is a kind of optimal choice of term for each germ that you can use to define the exponential height of the germ. Right? And when you do that, right, you get such a map, and it doesn't quite have the same properties as this one. It's not equal. Okay, so why is it not equal? Well, right, if I have a term that's bounded and bounded away, yeah, it's bounded, defines a bounded germ, and I apply the exponential function to it, the exponential height will go up by 1 because syntactically that's what I'm doing. But the level will not go up by 1 because applying the exponential function of bounded term is actually just composing it with the convergent power series. So they are not the same, right? There's a bit of a difference. But you can see why this could be important for our question of holomorphic continuations, right? If I want to describe the holomorphic continuation of a germ based on its representation by a term, every time I compose with exponentiation, I'm going to restrict the possible holomorphic continuation because exponentiation, right? If we go back to this picture, it will have a biholomorphic extension to this strip, but beyond the strip, it will not be biholomorphic anymore. Okay, so it's a bit of an exercise to think in the Riemann surface instead of in the plane, but it's a very similar picture to the plane where we also have exponentiation on the strip is biholomorphic, but when you go beyond, it becomes periodic. Right? Same happens here too, even though it's actually much bigger, right? This strip here corresponds to the half plane over there. So as a map from L to L, the exponentiation does extend biholomorphically on this strip, which is one reason why we like to work on L instead of C for this kind of picture. Yes?
Yeah, I have another question on your definition of exponential height.
Oh.
Yeah, just the example you gave, so you took a bounded germ, say if I apply the exponential, so the exponential height will increase. But the exponential function applied to bounded germ is a restricted analytic function.
Right.
So it does count nevertheless as one.
Sometimes it does, yes. Right. So it's just by when you look at the terms, the way we have to identify the germs with a kind of an optimal term, it can't be done quite as nicely as that to account always for the case that you're applying it to something bounded, because you don't, right? So it's not, that's the problem here, right? So the exponential height, you just can't quite define to always recognize that from looking at the term, right? That you are applying it to something bounded, okay? Anyway, so it's slightly different properties. So for example, the level is increasing on these germs going to infinity, right? The exponential height is not, because of course you can have something that starts with a power x, right? And then you have lots of small terms going to zero, very complex in terms of exponentials, going to zero very fast, right? So this guy here is not increasing. This one here is additive under composition. This one is not. Okay. So, but this one seems to matter when it comes to trying to describe holomorphic continuations, right? Because we have to look at a term to see how we can extend something, knowing that we can already extend something defined by a simpler term. Right. So the goal somehow is achieved by going by induction on complexity of terms, right? And so that's why we need this guy here as part of the game. Okay, so by the way, right, this level here we can extend to all of H. Level. At least to the positive ones, right? But I don't really care about the negative ones. Everything negative is the same in terms of holomorphic continuations. All right, so how do we do this? Right, if I have a germ F, which is bounded, but not going to zero, right? I set the level to be minus infinity. Remember, the level is increasing on these terms, and of course it goes down to minus infinity. Right? Higher the log, the lower negative the level is. So when you are bounded, right, it should be minus infinity. If F is say domination equivalent, in other words, in the same Archimedean class as 1, okay, and then if F goes to 0, it should just be the level of 1 over F. Right, which means as you go to 0, the level keeps going back up again. Right, so the faster you go to 0, the higher the level. And this extension of level preserves all the nice properties that level had on the germs in I. Okay, so let me see. What we have here then, right, is the following. You make a bit of an observation. right? So the most interesting thing to keep track of is what happens if we look at images of these kinds of domain and the log, right? Log we know has a holomorphic continuation to the almost entire L, right? In fact, it has a holomorphic continuation to all but L between, if you take away the segment here between 0 and 1, including 1, right? So as long as you take that away, the logarithm will have a holomorphic, even biholomorphic continuation to that. Okay. So what does this continuation do to these types of domains, right? Just for the log. And so it's just basic computation. Right? So if I'm applying it to a domain UF where F goes to infinity. So yeah, if F is in I, then applying the continuation of log to UF, so again, log bar is that continuation, that gives me another domain of the same kind, UG, right? Where, well, since log maps the half plane here, or sorry, this is 1. It maps this half plane into into the strip to the right of 1, right? I think it's maybe not this half plane, maybe it's the half plane at E. Yeah, okay, but it means that it, as a germ at infinity, right, it will collapse any big domain like that into a domain contained in the strip. Okay, so what I can say for sure is that G, this function here, is going to be either bounded or going to 0. Okay, but so there's a big collapse, right, under log. All big domains get crunched into something that's at most bounded, right? Where the boundary function is most bounded. But if you start with a boundary function that's already bounded, then okay, I'm cheating a little, but this is essentially what's true. What you get is that the image on the log bar of UF, again, is going to be a UG, where this time the level of G, the germ, the boundary function, right, is equal to, right, and since it gets smaller, but going to 0, that means the level goes up. Right? It's equal to the level of F plus 1. Again, well, of course, if the level of F is minus infinity, this doesn't quite make sense, but you get the idea. Okay, so that's why I'm saying I'm cheating a little.
I'm confused at this level. So, if you have function x plus e to the minus x,
yes.
it has level or something like that. Or
No, no, the dominant monomial is the one that will give you the level. Okay, there's level 0.
and e to the minus x.
But because of the e to the minus x, the EH is going to be 1.
But e to the minus x itself,
It has level, well, it's going to 0, right? So it's, in other words, it has the level of e to the x by definition, which is 1. Okay? Yeah. Anyway, so based on this observation, right? So we have to refine this a bit and be a little more careful, but based on this, we can define another size kind of level on the germs in H, which only makes sense if we think of these germs as being the boundary functions of these domains. Okay, So we can define something called angular level. I'm not giving the definition exactly because this is not precise, right? But we can define this angular level again on all positive germs. And this one takes values in n together with -1, not all of z. To represent the fact that log crunches all the big ones into something that immediately is bounded. Okay. So, and this, we can define it so that exactly the following holds, right? Every time I apply log bar to a UF, right? For every F in here, applying log bar to UF gives a UG with the angular level of G equal to the angular level of F plus 1. Okay, so the angular level will exactly do what we did here with a bit of cheating. Okay, and then of course for the X it will be the other way around. It will go down by 1. Okay, and anything like power functions don't change angular level, right? Power functions preserve angular level. Okay, anything polynomial preserves angular level. So this is kind of the very rough seeming sizing that we use on these domains to describe holomorphic continuations of germs. Okay, so now not every germ can possibly map these particular types of domains to other such particular types, like the log bar does. Power functions do, but there are other germs that don't. The reason is that addition doesn't make sense on here. Okay, so there's lots of germs that in fact would have holomorphic continuations very far, but they map domains like this into domains that are not exactly like this. Right? So we have to relax that notion a bit before we can describe holomorphic continuations. Yeah, I'll just have to start here again. Luckily, those other germs that have something to do with addition, right? They don't deform the domains too much. So the following definition is just right for this kind of game that we're playing here. So take K, a possible angular level. And let U be a subset of L, right? So something like that, but not quite, okay? So U is called a K domain if it's between, at least as a germ of infinity, between two actual domains UF and UG, where F and G both have angular level K. So if there are F and G, two germs, positive ones, such that the angular level of F and the angular level of G is equal to K, and UF as a germ is contained in U, which in turn is contained in UG as a germ. Okay, so that allows us for, you know, weirdness that happens when you bring in addition. So with that in mind, right, we also define what it means for a map from L to L to have angular level. Okay, so let phi be a map from some domain in L into L. So phi has angular level. So in other words, the word angular, the notion angular level is used both for germs in H, where it means something very specific, and then for germs of functions in L. Okay, has angular level k, and this can be any integer. Oh, angular level k, if for all sufficiently large, L greater than or equal to -1. Remember, the smaller the germ f in the UF, right, the bigger the level, the angular level. Okay, so for all sufficiently large possible angular levels L, phi maps L domains into L minus k domains. Oh, sorry, just two L minus k domains. Okay, so it like the logarithm will have angular level -1. Okay, in this sense. So the extension of the logarithm, log bar, will have angular level -1. X bar will have angular level 1. The extensions of power functions will have angular level 0. Okay. So that's for the logarithm bar, right? That's essentially what I was saying here. Just a translation of this. All right. So let's see, right? What we saw in the course as the continuation theorem was the following statement. Okay, so yeah, now I'm able to give you the statement again. So let f be infinitely increasing, an infinitely increasing germ. And now, right, there's two numbers. One is going to be defined using the exponential height of the germ, so the syntactic notion, but capped at 0. Okay, and the other one is the level of f. Let's call that lambda. So both of these have something to do to contribute to the holomorphic continuation of f. So then there exists a an eta -1 domain. Now that makes sense because eta is at most 0. So yes, at least 0, right? Yes, exactly. So this is at most -1. So it's an eta -1 domain U. There is also an eta -1 minus lambda domain V, and there is a biholomorphic map F bar. And now, of course, I'm running out of visible space. Yeah, I'll move it up in a bit. Okay, from U to V of angular level lambda. Right, so these notions very nicely let us describe holomorphic continuations of germs. Some biholomorphic extension to a domain whose size is determined by the exponential height of the germ. So the syntactic description of the germ. Okay, but the way it behaves, the images are determined by the level of the germ, right? It will collapse or expand, right? K domains to K minus lambda domains. So depending on whether lambda is positive or negative, it will blow up or not, okay? Okay, so that's the continuation theorem that we saw in the course. Well, maybe I'll keep the picture where it is. It's always helpful to have a picture. And we used this continuation theorem, well, in the construction of Ilyashenko algebras. I don't want to explain what that is, right? That was the motivation for using it. And one thing that we specifically that we wanted from it was the following corollary. So this is let's call this corollary 1, okay? So if you have a germ, again, infinitely increasing and of exponential height at most -1, okay? And in fact, right, we can translate the continuation theorem back to the complex plane in the following way, okay? You can find a positive number, A, and a holomorphic continuation now in a complex plane, but I'm still going to write H bar. Oh, no, sorry, what is this? H, F. Yeah, I'm going to use H and we'll see why. Okay. All right, so on some half plane, so that's the half plane, not H of 0, but H of A, right, to the right of real part equal to A. And now complex value, what does this do? This maps, in particular, every standard power domain. My standard power domains are all part of these UFs. Okay, so what it does, it maps every standard power domain. Standard power domains are a slight generalization of Ilyashenko's standard quadratic domains. Instead of having the power 1/2, you allow any power between 0 and 1. Okay, everything else is the same. So standard power domain gets mapped into every standard power domain. So that's a consequence of that theorem. And that's exactly the kind of thing that we needed to know in order to use such germs in the construction of Ilyashenko algebras. Again, I don't want to explain what that means, right? We wanted this kind of property. The problem was, right, which I did not get to address. Right, so this all works fine if the exponential height of my germ is at most -1. So it grows only logarithmically or slower. Well, at least from the point of view of syntax, right? The problem was that we actually need this for EH less than or equal to 0, not just -1. And H less than X. Okay, that's what we really need it for. And so that's what I want to address a little bit, this one problem. Why is this a problem? Why? You can see that if I take, for example, h equal to x squared, this corollary is false. Yeah. So example, even with EH less than or equal to 0, right? X squared has EH 0. But it doesn't do this, right? So the corollary is false for h equal to x squared. That's obvious because x squared already doubles the angular size of a domain. So it will not map the right half plane with this property. It will take standard power domains into something much bigger in the complex planes. Okay, so these two conditions seem to be crucial to get this corollary, but we don't get it from this statement right here. It's not precise enough. Okay. So I wanted to explain a bit how we do actually get it for these cases. And the reason why we do actually get it is because when you try to prove this theorem, the continuation theorem, right? You want to prove this by induction on complexity of terms defining the germ. Okay. The theorem doesn't say enough to be able to drag along the full induction. In order to get through the full induction, you need to add additional properties or regularity properties that you need to keep track of that will allow you to get through the full induction. So the motivation originally for getting a better continuation theorem was purely because we couldn't prove this directly. Right? But turns out that it is also very useful for these kinds of corollary afterwards. So let me describe. How much time do you have? Doesn't really matter. Does Anyway, so there's a couple more regularity properties, and they're not actually all that hard to describe, but they make a crucial difference. Right, the kinds of holomorphic continuations that I'm describing there, well, I want to define a class of maps that based on this kind of functions that we get there, okay? But they have a few extra properties as well. So fix some eta, natural number, think of that eta over there, and fix a lambda, an integer, again, think of the lambda over there, okay? Assume lambda is less than or equal to eta, which is the case because we know that the level is always less than or equal to the EH. Okay, that's not hard to prove, but you need to prove it by some sort of induction. And now, again, let's say we're given a map phi from U to V on the Riemann surface. So this phi is called an eta lambda map, for lack of better terminology, if three conditions hold, right? So the first condition is essentially what we have in that continuation theorem, okay? So U is some eta minus 1 domain. V is an eta minus 1 minus lambda domain. And phi is biholomorphic of angular level lambda. Same as exactly the portion of the continuation theorem. Okay, but then we want a couple more things. That's actually true for all of the examples I mentioned. You can easily check these things, right? So not only does it map k domains to k minus lambda domains, right? It never maps them into smaller domains. Okay, so I want to also say that. So for any k greater than or equal to eta minus 1, and every k minus lambda domain. So this is kind of a property, right, that makes you go to the compositional inverse. Say something about the compositional inverse. So I have to include that. So if I have a k minus lambda domain contained in the image of phi, okay, then you can find a k domain u prime in U, which gets mapped to V prime. It's just the precision on the notion of angular level. Seems quite innocent, but it's necessary for the induction. And there's one other thing. Well, there's two other things really. But one thing is that in fact, the growth rate of these functions at infinity is also controlled, right? And the way you think it should be. Like, so you can find, right? We have said we have lambda, right? That's the angular level of the map, right? So there actually exist germs H1 and H2 infinitely increasing of level, or why infinitely? Oh yeah, infinitely increasing because phi, right, is a germ at infinity, yes, and goes to infinity. Okay, so of level, both of level lambda, such that, right, the modulus of phi of x is wedged between h1 of the modulus of x and h2 of the modulus of x. Okay, for all sufficiently large x in U. So the growth, the complex growth rate, or is the same as the real growth rate. That's what you would expect. Okay, we don't say that there, but it's actually the case. And so then there's this one little extra property that I want to keep track of, right? All these extensions have the property, of course, that along the real axis, they're real valued, right? And since these domains are connected, simply connected and all that, they're split in half. They're separated by the positive real line, which means these holomorphic extensions can only map points above to points above, or all points above to points below. Right? It's one of the two. You can't have some points up here mapped to up and others mapped down. Right? But which is it? Is it going to map things down or up? Keep them upstairs or not? Right? So we need to keep track of that too. So definition. So phi, same situation, right, is called angle positive if it maps, if the argument of x and the argument of phi of x have the same sign for all x. So it maps the things above to above and the things below to below. It doesn't somehow flip the picture. Same sign for all x. Okay, and of course, angle negative would be the opposite. So it's opposite sign. Okay, so for example, right? Yeah, log x power functions for positive powers all are angle positive. But if something is angle positive, then its reciprocal is angle negative and vice versa. So negative powers are angle negative. Okay, so this is something that's reversed under taking reciprocals. Very simple property, but it's actually crucial for a refinement that we're looking for. So I can now give you the full continuation theorem. And I'm going to save a little bit of time here by just cheating. This is not recall anymore. This is just the full theorem, which is, again, under the same same assumptions, there exists. And now, of course, it looks actually much shorter. For all such germs, there exists an angle positive. Eta lambda extension. F bar of F. Okay. So the full theorem looks shorter, but of course, yeah, it's all the stuff over here. That's it. That's it. It's taken into account. And so how does this actually improve what we were trying to do there, right? We get a version of this corollary that's more precise. Okay, so I'm going to erase that now. I'll give you that version because I still have a couple of minutes. So for complex continuations, that's not for all the germs, of course, only for the ones where EH is at most 0. Okay. So F infinitely increasing and EH of F. No, again, I want to use H like before. Is at most 0. Okay. So then in terms of complex, what this implies over there is that we can find again a right half plane and the what is it? Yeah, okay, here I only say holomorphic continuation, H bar. Most of the time it will be biholomorphic, but I got to be a little careful because of only that assumption. So holomorphic continuation with the property that 1 over H bar is bounded. That's just because like the image of H bar is a real domain. So 1 over H bar is going to be bounded. Okay, so that's one way of expressing that fact in the complex plane. Now this H bar of X in absolute value will go to infinity. Okay, as Z goes to infinity in absolute value inside the plane. Okay, that's also from this, right? That essentially a corollary of that. And this is the crucial one. If F is actually dominated by X squared, remember X squared is that bad counterexample, but below that, right? So X squared, right? It blows up the half plane only to the full plane minus the negative real axis. So that's still good. There's no overlap. That's why X squared is kind of the cutoff for my description here. It's just because of that. So I don't have to go to the Riemann surface to describe what's happening here. Then the image of the half plane is just like for any power less than X squared, is contained in the complex plane minus this minus infinity to 0 segment, half line. H, yes. Okay. And in this case, H bar is biholomorphic. Yeah, so there it comes. It's not quite true, the biholomorphic part there in general, because of the higher powers. Okay. Biholomorphic onto its image. And if I take any point in the half plane, we have the following condition, and that condition comes from the angle positivity. Okay, the sign of the argument of H bar of Z is equal to the argument of Z. It preserves the argument. Sorry, the sign of the argument. Meaning it maps things above the real axis to above the real axis and things below the real axis to below the real axis. Okay? Doesn't sound like much of a difference, but that's actually exactly what we need to get corollary 1 for functions for germs like this. Sorry? Ah, okay. Well, okay. Yeah. No, I guess I will explain it to anyone who wants to see. It's a very simple argument after this, right? But yeah, this is really what we needed in order to get everything. And somehow this property here seems very innocent, but it's very useful. Okay, thank you.
Thank you very much.